In oscillation, you have something called resonance. Resonance is a phenomenon in which a system responds at maximum amplitude to an external driving force when the driving force frequency is equal to the natural frequency of the driven system. So to put it simply, for example, I give you a trolley that is held on a horizontal surface by means of two stretched springs. This is your trolley, and then these are your two springs. So one spring is attached to a fixed point, which is over here, while the other spring is attached to an oscillator that causes horizontal oscillation of the trolley. This is your oscillator here, okay? So from here, we tell you that the frequency of vibration of the oscillator is gradually increased from a very low value. So the thing here is this, your oscillator here, if you switch it on, it will apply some sort of driving force onto the spring, which in turn pushes onto the trolley, which in turn causes the whole system to oscillate, right? So your oscillator here, when it applies your periodic driving force, it will apply at a certain frequency. Let's call this frequency FP, driving frequency, okay? So your oscillator applies a driving frequency on your trolley, causing your trolley to oscillate at the same frequency as your driving frequency. So you go and increase the frequency of your oscillator and hence trolley from a very low value to a very high value. And then after that, you measure the variation of the amplitude of vibration of the trolley with its frequency and plot a graph. The graph that you see below here is the graph that you're supposed to get. This graph is called your resonance curve. So you will notice one particular thing about this graph. The graph, as you will suddenly reach a peak and then after that it will drop down, okay? You'll notice that the amplitude of oscillation of your driven system, which is your trolley here, will increase to the maximum and then after that it will drop down, right? So the point where your amplitude reaches a maximum is of interest to you. This is where you have maximum amplitude. So the point where your system reaches maximum possible amplitude is when your driving frequency from the oscillator equals the natural frequency of the driven system. Now, just now, before this, I told you that doesn't matter whether something is a free oscillation or a forced oscillation system, they all have their own natural frequency, just that natural frequency is more readily shown in a free oscillating system. So for your trolley here, your trolley actually has its own natural frequency of vibration. It's just that when your driving frequency applied by your oscillator is equal to your natural frequency of your trolley suddenly starts to oscillate with maximum amplitude. That is what resonance is. To put it in a simpler explanation, at resonance, a system will oscillate at maximum amplitude when driving force frequency equals the natural frequency of the system. That is what resonance actually is. Now, after that, if you go and increase the driving frequency further, the amplitude of oscillation of the driven system will start to decrease. That is what gave you this characteristic curve here. All right. Now, what happens when you try to introduce damping into the system, or rather you increase damping to the system as it oscillates? Now, increasing damping to your system actually will produce three effects on your resonance curve. There are three changes that you expect to see. If let's just say just now, when we started oscillating the trolley, this was your original graph at light damping. What if you increase the damping? Okay, if you increase the damping, this one is damping increase. What you expect to see for the same resonance curve is based on these three. Number one, your whole graph line will become lower. Okay, you get a graph of lower peak. So with critical damping, let's just say it's an increased damping case here, your whole graph becomes lower. And then after that, your graph will become flatter. Okay, your graph must become flatter. Now, what do we mean by flatter here is something like this. If I try to redraw the graph for you, let's say that this is your resonance curve. If I had mentioned to you that your original graph had looked like this, and then I said that there's increased damping in the system, so I know that the whole graph must be lower. But what if I drew my graph like this? The graph is lower. Okay, the graph is lower, which is what I want, but is sharper. This is not what you want. You see, if you just look at the peak of the graph for the green line, it's actually sharper than the red line. So if you had tried to draw the graph with increased damping like that, you got one part of it wrong. It's not supposed to be sharp. It's supposed to be flatter. So if I wanted to draw it correctly, this one being the original line here, if I wanted to draw it correctly with increased damping, it should have been something like this. This one, the graph is lower, correct, and flatter. This is what we want. So that's why here there's a second criteria where your graph must be drawn flatter than the one before it, okay? And then after that, the third criteria here would be where you say that the frequency at which your maximum response occurs also decreases where your graph shifts to the left. The maximum response here that you're talking about here is the point of maximum amplitude. Is the point where you have max amplitude. Okay, if you look at the original graph, the one with light damping, where you had maximum amplitude, it was right over here, right? But then after that, with increased damping, you will notice that the point where you have maximum amplitude starts to decrease. The frequency at which it occurs starts to decrease. It shifts towards the left, like this one here. Isn't it? So it kind of goes towards the left. The frequency at which maximum response occurs decreases because the graph shifts to the left. Now, why does this occur is mainly because of this. Is because with damping, with more damping, your system oscillates slower. So it takes a longer time to complete your cycle, to complete one oscillation. So it oscillates slower, period is longer, therefore frequency is lower. That's the reason why it shifts towards the left. But when you're asked to draw the graph in your exam questions, the examiner is really only looking at point number 1 and point number 2. Now, point number 3 is optional to be shown. You can show it with the frequency shifting towards the left. You can show it as being unchanged, still at the original frequency. It doesn't matter. The examiners accept both answers. You can show it as being shifted towards the left. You can show it as being unchanged. Either one, the examiners will accept both. But what is more important is that you must follow the first two criteria. These two is actually important, okay? Then last thing I should probably mention to you is this. The graphs that you see here all have damping inside, from light damping to critical damping to heavy damping. What about a case where you have no damping? Now, if you have no damping, your resonance curve will have an infinite peak, okay? So what I mean by that is that if I try to draw a graph with no damping, it by right should look like this. You see, there's no peak that you can see to your curve. It goes on to infinity. This one is with no damping. If no damping is involved, your peak is going to be infinite. All right. So have a look at page 4 of your notes. This is the only part remaining that I haven't discussed with you. Okay, it's a continuation from resonance. So for resonance examples, you should know some examples where they are not useful or examples where they should be avoided. Now, take for example, during an earthquake, you want to avoid resonance of your building. What I mean by that is that if you assume that maybe the yellow colored line that I just drew is your ground, and then you have a building right on top of it, this building that you have has its own natural frequency. But when you have an earthquake, you know that during an earthquake, the ground shakes. So during an earthquake, the ground shakes. It could be shaking up and down, or it could be shaking left and right. It is actually oscillating. If the ground is shaking with a certain frequency, it's actually causing some sort of driving frequency onto your building. But the building itself has its own natural frequency. If you're unfortunate enough where the driving frequency is equal to your natural frequency, your building will actually start to oscillate, but with the largest possible amplitude. So when it oscillates with the largest possible amplitude, like the ones that's being shown here, it will actually cause your building to collapse because it's made out of rigid concrete or brick. You cannot really bend concrete or bricks, right? So you try to make it oscillate with a very large amplitude, you try to bend it, the whole structure will actually start to break. That is because if during an earthquake, the frequency of ground shaking, if it's the same as natural frequency of your building, you have large amplitude of oscillation, your building will start to collapse. All right. Now, to prevent this from happening, you normally design your building so that the natural frequency is very much different than the frequency of the ground shaking during an earthquake. So people have collected data over the years for the earthquakes that occur all around the world, so they roughly know what are the frequencies in which the ground shakes. So they can actually design the building so that the natural frequency is far off from those frequencies. Now, you can also try to modify your building a little. You can actually build steel columns into the building so that it's actually more ductile and can bend without breaking. What we mean by that is that you actually drive in some sort of steel column into the building like this so that it strengthens the building so that your building can actually bend a bit more without breaking. Okay, this is one example where resonance should be avoided. Now, another example where resonance should be avoided is when you're designing a bridge. So if you look at the suspension bridge that's right over here, a simple diagram of it could look like this. Let's assume that it has a rectangular cross-sectional area like this. This one is your suspension bridge. It has a rectangular cross-sectional area. Now, because it's suspended over a lake or some sort of river, it will be subjected to wind. So say, for example, you have a wind that's blowing right across like this. But because your bridge is having a rectangular cross-sectional area like this, the moment the wind hits the bridge, it can't really flow past it. Instead, what will happen is that it hits the bridge and then it turns back. So this motion of continuously hitting the bridge and turning back causes some sort of oscillating force, some sort of periodic force on the bridge. So here, right now, your wind is actually applying some sort of driving frequency onto your bridge. And your bridge itself, again, has its own natural frequency. So if it just so happens that your driving frequency equals your natural frequency, you have resonance. If driving frequency equals natural frequency, resonance occurs. So when resonance occurs, your bridge will start to oscillate, but it oscillates with the largest possible amplitude now. So same thing like the case of the building. If you try to bend your bridge too much, it will start to break apart. So this is another example of resonance that you want to try to avoid. Now you read the notes the first part here, I mentioned that when wind blows across the deck of a suspension bridge, the turbulent winds known as eddies are formed that can cause the bridge to twist and oscillate. The wind hitting the bridge and then turning back on and off, that one is known as eddies. But this term here is actually not really something that the syllabus expects to see. I mean, when you go and write your answers, they don't expect you to write the term eddies. Because later on in AC circuits, which is another A2 chapters, you have something else called eddies. That one is another different things. Okay, so here I also mentioned something called eddy. It's a different thing. So don't need to bother so much about the term eddies here that I mentioned, because later on in AC circuits, there's some other same term that means something entirely different, which you need to know. So back to what I was talking about, the winds cause oscillation equal to the natural frequency. If the winds cause oscillation equal to the natural frequency, your deck will start to have large amplitude oscillation and break apart. So to overcome this, what you do is that you design your bridge to be aerodynamic so that wind can flow above and below it without forming eddies, so that your wind doesn't just simply turn away back and forth. So when we say your bridge must be designed to be aerodynamic, it means something like this. Let me just redraw the diagram. It could mean something like this. Rather than having a rectangular cross-sectional area, you may have something that looks like this, looks like some sort of hexagon, where you have some sort of sharp edge here. So when you design your bridge like that, when wind tries to blow across it, it won't just simply hit it and go back. It can actually flow right on top of it and right below it. So because you're allowing the wind to flow past your bridge, you don't have any eddies. You don't have any kind of oscillating force caused by your wind. So you are avoiding any kind of possibility that resonance occurs. So this is what we mean by designing the bridge to be aerodynamic. Okay, so whatever I just mentioned here are cases where resonance is actually not useful and should be avoided. There are also cases where resonance is useful. Okay, you need to know one or two examples where resonance is useful. The most obvious example would be for your microwave oven. Your microwave oven is a useful example of resonance. So how does your microwave oven actually work? So I'll say this is your microwave, like this. And then after that, you have some sort of food inside. This is your food that you put inside your microwave. Your microwave, as the name implies, it uses microwaves to cook your food. Your microwaves have a certain frequency. Let's call this the driving frequency. So how does your microwave actually cook your food is that when you're talking about food, food normally has moisture inside. It is moist to a certain extent. So it must have water molecules inside. If there's some degree of moisture inside, you must have water molecules inside your food then, if there's some degree of moisture. So the thing now is that you have H2O molecules inside your food, and those molecules itself are actually vibrating. So when they vibrate, they are vibrating at their own natural frequency. If your microwave, the frequency of your microwave is set in such a way that is the same as the natural frequency of vibration of the water, this will cause your water molecules to vibrate faster, hence generating heat to cook the food. If you remember the ideal gas chapter, there's a relation between kinetic energy of your molecules with temperature, right? That one was actually this one. Mean kinetic energy is actually 3/2 kT. So here, when your water molecules are forced to vibrate faster, your kinetic energy is actually increasing. This in turn causes your temperature to increase. So you now have heat to cook your food. Okay, it's related to what you learned in ideal gas. This equation is from your ideal gas chapter. So when driving frequency equals natural frequency of your water molecules vibrate faster, you have heat generated to cook your food. So that's for this. Now, for the last two sentences where they talk to you about in the radio or television, an electronic oscillator oscillates at the frequency that matches the signal frequency that's to be received from a radio or television station to allow effective reception of the signal. This one don't bother about it because this is no longer in your syllabus. It used to be in a chapter called communication, which has been removed from your 2022 syllabus. So this one don't bother. Just remember the example for microwave and you'll be fine.